Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video we're going to go over the conjugate zeros theorem. If f of x is a polynomial function with real coefficients, and if some complex number z is a zero, then the conjugate of z is also a zero. So conjugates have the same real and imaginary parts, but the sign of the imaginary part is different. So for instance, if z was 6 minus 5i, the conjugate of z, which we can write with a bar above it, that's going to be 6 plus 5i. And what this theorem is telling us is that if we know one of those is a solution, we know the conjugate of it is also a solution. Another example of conjugates, if z is 3 plus 4i, its conjugate will have an imaginary part that's negative 4i instead. Now, this theorem, we've been finding real roots in algebra for a long time, and this doesn't contradict what we've been doing so far. If x equals 7 is a zero, is its conjugate a zero? Well, x equals 7 can be written as 7 plus 0i. The conjugate of 7 plus 0i is 7 minus 0i, but both of these are still just equal to 7. So the conjugates by default, when the solution is real, the conjugate is the number itself. So it doesn't violate this theorem. We can use this, though, if we know one complex non-real solution, we can get another one for free. Find all zeros of f of x equals 2x to the fourth minus 15x cubed plus 18x squared plus 90x minus 200, given that 3 plus I is a zero. So I'm going to use that fact right away with some synthetic division. 3 plus I, we're going to divide that into 2 for x to the fourth, negative 15 for x cubed, positive 18 for x squared, 90 for x, and negative 200 for the constant term. Bring down the 2. 2 times 3 plus I is 6 plus 2i. Combine the real parts. Negative 15 plus 6 is negative 9. Bring down the 2i. Now this is where this is going to get a little tedious. 3 plus I times negative 9 plus 2i is negative 27 plus 6i, just using FOIL style multiplication. Plus I times negative 9, that's minus 9i. I times 2i, that's 2i squared. 2i squared is really negative 2, so this becomes negative 29. 6i minus 9i is minus 3i. So I'm going to write that down, negative 29 minus 3i. Combine the total of the column. 18 and negative 29 combine to be negative 11 minus 3i. I need to multiply again. 3 plus I times negative 11 minus 3i. Use that FOIL style multiplication again. 3 times negative 11 is negative 33. 3 times negative 3i is negative 9i. I times negative 11 is negative 11i. I times negative 3i is negative 3i squared. That's the same as negative 3 times negative 1, or really like positive 3. So negative 33 plus 3 is negative 30. Negative 9i and negative 11i, those combine to be negative 20i. Write that down, negative 30 minus 20i. Total the column, 90 and negative 30 combine to be 60 minus 20i. One more to check. One more product to do. 3 plus I times 60 minus 20i. Now, this should give me a positive 200 because I need to get a remainder of 0 or it's not actually a 0, and I was told that it was. 3 times 60 is 180. 3 times negative 20i is negative 60i. I times 60 is plus 60i. I times negative 20i is negative 20i squared. The I terms add to be 0. Negative 20i squared is the same as positive 20. 180 plus 20 is 200. Remainder 0. So there is one out of the way. And now I've got it down to a cubic polynomial. I need to do the same thing now with 3 minus I. So first thing I'm going to do is I'm going to clear up some room. If you need any of this, just pause it, rewind to this point. I'm going to get rid of it though. And I'm going to do the second step in a different color. 3 plus I, oh, I'm sorry. 3 minus I is the conjugate, and so that's also a 0. And that's going to go into 2, negative 9 plus 2i, negative 11 minus 3i, and 60 minus 20i. Oops, sorry about that. Let's bring down the 2. 3 minus I times 2 is 6 minus 2i. Total that column. Negative 9 plus 6 is negative 3. 2i minus 2i, that's 0. So that is just negative 3. That makes the multiplication a little easier this time. 3 minus I times negative 3 is negative 9 plus 3i. Total the column. Negative 11 minus 9 is negative 20. Negative 3i plus 3i is 0, so we just have negative 20. Multiply one more time. Negative 20 times 3 minus I is negative 60 plus 20i. Everything here adds up to be 0. Perfect. So now we've gone from having to set that fourth degree polynomial equal to 0. Now we've got a second degree polynomial equal to 0. We've got it down to 2x squared minus 3x minus 20 equals 0. And again, if you can factor quadratic expressions, the finishing step here is going to be easy. This is actually going to be 2x times x, and 5 and 4 are the two numbers, and the 5 is positive and the 4 is negative. If you FOIL that back out, we see the 2x squared, we see the negative 20, but outside is negative 8x, inside is positive 5x, that makes negative 3x. So what are the other two roots? I'll start with the easy one. I know that that's x equals 4. For 2x plus 5, that means that 2x plus 5 is 0, or 2x is negative 5, or x is negative 5 halves. So the zeros are 3 plus I, 3 minus I, negative 5 halves, and 4. The first division was painful. The second one, since we're getting back to just real coefficients, was less painful because the I terms, the imaginary parts, kept canceling out. And then we took it from a fourth degree term polynomial to a second degree. Not so bad. That's it for this one. When we come back, we'll talk about a way of determining what kind of solutions we might have.